And we're live. Thank you for joining us for the second panel discussion today in the AI Tech Symposium. Uh, right now, we're going to discuss designing graph rag architecture. And I know that some of the hottest buzzword or buzz terms that is going on in the semantic space and the development of richer information retrieval. So we're going to do our best to dive into the bones and the critical components of this architecture. But before we get into the discussion, I would like to just go around the list of panelists so that they can introduce themselves and sort of their background and what they've done. I think that'll paint a much richer perspective as to how we're going to cover this topic holistically. So with that, George, would you like to kick us off?
Hi. Thank you for having us here, Joaquin. I am an information architect, which means that I structure digital experiences so that information can be more easily found and understood by people. So that means understanding how people think about things, what they need to know to get certain things done, and then structuring the information so that they can make the most use out of it. I've been doing this kind of work for around 30 years now. It's been a while, and I've authored several books, including I've co-authored the 4th edition of the O'Reilly Polar Bear book on information architecture. So this is very much my focus. I will say up front, I think that we were talking before you went live, and I think that I'm the least technical member of this panel. And that's, but part of the reason why I'm here is because I am very cognizant of the fact that technology has a huge impact in how people access information, and I'm incredibly excited by what's happening with AI, and I have been experimenting hands-on with several of these technologies, and we'll probably talk a little bit about what that entails. But my primary focus, and part of the reason why I'm here, is because I want to learn about how to better use these technologies so that we can create better experiences for people. So that's my intro.
Thank you, George. We're just going to move on to Matteo. You can give a brief introduction as well.
Yeah, for sure. Matteo Casu, I'm a semantic engineer at Semantic Partners. That is a consultancy company specializing in semantics. We are integration partners for a number of vendors, especially for RDF triple stores and data catalog platforms and the like. My original background was in philosophy. I graduated in philosophy, but then because semantics was my passion, and because I wanted to see some more concrete application of these things, I became a software engineer along the line. I've worked in both in consultancy, project-based companies and product companies. I've been project analyst, tech lead along the way, but my interest has always been in knowledge representation, first and foremost, and semantics in general. Now at Semantic Partners, we are trying, among other things, my role at the moment in these last 6 months or so has been to explore how you can conjugate LLMs and knowledge graphs together, because obviously there is a lot of hype around this particular topic, and there's a lot of questions from clients. And we think that is both a professional and ethical challenge to for us as consultants to understand these things as they come to the front, so that we can help our clients and partners to understand how to use them in the most sensible way. And this is what we are trying to do at the moment, and I'm very happy to be here sharing this with you today.
Thank you, Matteo. Prasad, would you like to give us a little bit of a background?
Thank you so much for having me here on the panel. My name is Prasad Yalamanchi. I'm the founder CEO of Lead Semantics. It's a developer of TextDistill. It's a language to knowledge graph product, and it's pretty apt at the subject area that we are covering here on the panel. I have a background in computer science, and more importantly, my critical years in forming my skill set in probably more than 20 years of IT computer science experience has been in the areas of language and knowledge. And I have similarly 20 plus years in the areas of knowledge engineering and machine learning and distributed systems and parallel systems and similar stuff. But recently, though, I have been working with automated language understanding and knowledge graphs and ontologies and LLMs, um, and hence we are into developing this language and knowledge product. It literally extracts knowledge from unstructured data into knowledge graph and then serves up in terms of queries and all of that, which is pretty much part of what graph rag is, or a knowledge graph rag is what we call it. For I would like kind of discuss further on during the panel. That's my background.
Thank you, Prasad. Moderating this panel is George Aniadotis. What I've been doing this year, he's been doing 10 times the amount plus. So you guys are in good hands. George, would you like to give us a brief intro?
Yes, thank you very much. And well, first of all, my apologies everyone for being a bit late, but Joaquin, besides having given me a very warm introduction, he also did part of my job, so introducing people. So I can do my own intro, and then we can take it from there. So yes, I'm George Anadutis, and pleasure meeting you, everyone in the panel and everyone in the audience as well. And well, let's see the quick story. I give the very quick version of my background here. So let's just say that I started my career in terms of background. I'm like a hardcore software engineer. So I started my career producing software. I moved on to consulting and managing people who produce software, and now I'm at a stage where I talk about other people who do these things mostly. So I work these days more as a freelancer and a consultant, analyst, and all of those things. But enough about me. Let's actually get in the midst of the conversation here today. So since we're talking about RAG and graph RAG, probably a good place to start would be to actually define that. But in order to define that, actually, I did a little bit of exploration on the topic myself on the occasion of having this conversation today. And obviously, the best place to start if we want to talk about graph RAG would be RAG, so retrieval augmented generation. It's part and parcel of working with large language models. So I guess let's take a step back and try to trace how these large language models came into our life and what is RAG and why are people so much interested in utilizing this technique, and what does it have to offer that sort of makes up for some of the limitations of large language models. So anyone with an opinion on this, feel free to go, and we'll take it from there.
Yeah. I'll start off. Thank you so much, George, for handling, mediating this conversation here. I think that was a pretty good intro question that kind of, sets the ball rolling. So large language models clearly, are exposed to the widest amount of data on which they are trained, and so they are expected to be predicting, and generating language, and in doing so, we are all aware of the weaknesses, so-called, of these large language models, that they confabulate and they are not really specific to a particular domain. So those are well-known problems, rather weaknesses. I mean, clearly there is use for what they do in particular situations, but beyond that, there is definitely they can be termed as weaknesses that need to be fixed or addressed one way or another. And RAG is one of those systems, where the domain specificity can be addressed by giving it a specific set of data all related to one single domain, for example, or a subject area, and that allows for limiting the LLM to kind of, focus on that, newly fed data to generate its answers and all that. And given that it is focused to a narrower set of documents, the level of confabulation is also reduced. And for whatever is the reason, it definitely reduces and addresses these two very important weaknesses, so to speak. And hence the case for RAG. And RAG does not, as we have experienced with the RAG has certain weaknesses in and of itself, based on, again, the kind of technologies that are used to kind of build the RAG systems themselves. They don't have the comprehensiveness of covering the entire corpus, for example, given they are limited to producing certain number of results and so on. And then, given the similarity matches and cosine similarities and things like that, like the vector matches, inherently, you are just looking for, matches between the string equivalences and, things like that, with the associated, meanings that are encoded in these indexes. And so to go past that, a graph RAG is one, it covers the entire corpus, given that, there is an intermediate step of creating these relationships across all the entities that are found spread across the entire corpus. That is one, stretch of computation that covers the entire corpus, produces this entities and relationships among themselves. And then that is what is now the fodder for the second step of generation. And as such, it becomes such a curated data set already, a second set of curation that allows for far richer navigation through all these interrelated information that is already connected. And hence the results are so much more accurate, and the coverage is there, it is comprehensive, and you can, and probably through the course of rest of the discussion, we can address some of those things.
Yeah. So Prasad already mentioned something that I'd like to throw out there for any of the rest of you to pick up on. So he talked about well, text and how you can get textual correspondences or correlations, and I think that touches on a key concept if anyone needs to understand what RAG is about, and by extension, graph RAG, which we'll come to address shortly. So vectors, basically, this is a key concept to understand how large language models work, how any machine learning model works for that matter. But since we're interested mostly in large language models now, this is the key. So would anyone like to give like a 2-minute explanation of what vectors are and why vectors are so relevant for RAG?
Maybe I can
the
try.
Key concept that, yeah, go ahead. Yeah.
This is not part of my specialty, of my background, but it's actually something that I managed to learn. So hopefully I can give a fresh point of view of the layman in a sense. To me, embeddings of words into vectors are particularly interesting because I come from philosophy of language and from how to capture the semantics of words. And there are so many ways, so many points of views that you can adopt when you try to capture the semantic of a word or of a concept in a computational way. And now the dream of embedding and vectorization, I think it came about in the first 2000s with algorithms like word2vec, for example, is that you can take a corpus and you can measure the co-occurrences of words between each other. So if a word happens to be many times with another word in terms of vicinity in the text, for example, it means that there is a stronger correlation also semantically. And this is a very old idea, very ancient idea, actually. And the discipline study this is distributional semantics, which is a subfield of computational linguistics. And the idea is that you take all these words and you represent them as vectors in a multidimensional mathematical space where each dimension corresponds to the proximity or vice versa to the distance of that word with any other word. And I think a very simple example to understand this very powerful idea is that by using these techniques, you can capture the fact that if you represent the word for queen and king, for example, you can, and male and female, you can demonstrate that in this mathematical space, the following formula holds. You can have that queen is equal to king minus male plus female. So if you take a king, you take away the male concept from it, and you add the female concept to it, you get a queen in terms of vectors and the distance between vectors. And this means that this mathematical framework is able to capture a very powerful aspect of our language and of our semantics. And this is why sometimes I enter into polemics with my own colleagues from my own space, because in the semantic space, some people are very affectionate to the idea of symbolic AI and representing everything with only with symbols and rules and axioms, and not with statistics. But the thing is that even if I also come from a symbolic AI background, we have to accept the idea that statistics went a long way in capturing at least one aspect of how our language works. And again, this is not something new. Symbolic AI and statistical AI have both a very respectable and ancient lineage. They were born pretty much at the same time, more or less between let's say in the 1960s, just to simplify it a bit. And I believe at the time it was Marvin Minsky, one of the great grandfathers of AI, who called these two flavors of AI the scruffy and the needs. So the scruffy were the AI scientists using statistical methods, and the needs were AI scientists using symbolic methods or using mathematical logic, for example. And to this day, you can recognize these two flavors of how to do AI in how we do things even nowadays. The great thing about semantics in 2024, I think, is that we are approaching that moment when the two things start to come together, because we have a powerful representation of words in terms of vectors, as we just said, and that's the idea of embeddings and the vectorization of semantics. But we also have ontologies and knowledge representation and reasoning, which is the whole tradition to which I myself belong, of representing meanings with symbols and axioms in a very neat way. So I think that in our generation time, we will see probably the convergence between these two very old and competitive, let's say, branches of the AI tree. And this is going to be very interesting. Sorry, I took a little bit of a tangent, but hopefully it was still on topic.
Yes, absolutely. Actually, I got more than what I bargained for, because I just asked for a quick definition of vector, and you expanded from that to give us like a brief history of symbolic versus statistical AI, which was also in our list. So that's covered now, I guess. So, okay, I'm going to switch then to you. Is it Jorge actually, or how do you pronounce it?
You can say either, but I usually go by Jorge.
Okay, I thought so. All right, so I'll go with Jorge. It's easier for me as well. So, Jorge, I guess then, would you like to pick up from where Matteo left and just try to get to? I'd like to ask you basically if you'd like to share with us how is this whole vectorization process? How is it relevant to RAG? Because I think Matteo did a very good job of explaining what it is and how it comes into play into large language models, but it's also a key concept for RAG itself. And after we have addressed that, then we can start from there to actually get into the main course, which is graph RAG and how it differentiates from baseline RAG.
Sure, well, like I said at the top of the conversation here, I am the least technical of the folks on the panel, so I'm probably going to do the most injustice to these ideas, right? But when I was hearing Matteo talk about it, I thought back to what Prasad was saying earlier about the role that RAG plays in general, right? So when thinking about these two systems, the statistical AI versus symbolic AI, the way that I have understood the things like language models to work, and again, this is very much kind of like a lay person's understanding, is that what is being captured are statistical, the statistical likelihood that one term will be related to another term, right? So I think that there's a difference, and this is the language that I've been using. I think that there's a difference between a reasoning system, a system that is able to reason, and a languaging system, right? A system that allows you to work with language in ways that produce useful results or can produce useful outcomes to certain queries, but is not necessarily reasoning behind the scenes, right? And the way that language models work, and you can experience this if you interact with something like ChatGPT, is they've been trained on statistical relationships between terms in general. And with something like RAG, you are narrowing, you're saying leverage the relationships you know about between terms, leverage them within this particular context, right? So you're providing it with a corpus that has a particular set of semantic terms, and I'm saying that rather than saying ideas, because I think that that's where the ontologies that Prasad was talking about earlier come in, right? When you actually start associating terms and assigning types of relationships between them, you're going a step beyond merely finding the statistical likelihood that one term is related to another, and actually assigning particular types of relationships between them. And that might be wrong, and if it is wrong, I would encourage my other co-panelists here to correct that, because again, I don't have as deep a technical insight into it. But what it boils down to your question, George, what it boils down to is you should be able to get much more relevant results out of an interaction with a system that understands something about the nature of relationships between semantic terms than if you're just looking at a system, or if you're just interacting with a system that knows about statistical likelihood between terms. Does that make sense?
Yes, it does. It does make perfect sense. I mean, to put it in a very simplistic way, what you're basically doing, what an LLM is basically doing, is sort of exploring this vector space that it has built during the training phase. And with RAG, what you're doing is you're extending, but also making more specific this search space. Mm-hmm. You're instructing your LLM to look for results in this particular subset of this search space, so to say. That's a very as a simplistic explanation as I can think of, at least.
Which should lead to more relevant results, right? To Prasad's point earlier, reducing things like hallucinations or confabulations and stuff like that.
Yes, indeed. I mean, no matter how big or well curated corpus you have used in the training phase, and how sophisticated that training is, experience so far goes to show that the nature of the underlying architecture of how this LLMs is built will always lead to at least some amount of confabulation or hallucination or whatever it is to call it. So RAG is basically an attempt to limit that as much as possible, and at the same time make the results more specific and tailored to your particular interest and your particular documents or database or whatever it is that you want to explore. So that all said, I guess it's a good point to now address what does graph RAG bring to the table as opposed to vanilla, let's say, RAG, which is based on vectors? So the idea in RAG, again, very simplistically, is fine. You have your initial vector space created during training, and you expand it by adding an additional vector search space that you specifically provide. So how is graph RAG different?
Can I take a shot at it?
Sure, go ahead.
Yeah. So just the plain RAG, I think, we have clearly given good definitions among our renditions of it, what a RAG system is bringing to table over and above a regular LLM. What RAG does do is this vector search, and as you all rightly kind of, brought it to the point of, limiting the search space so that it is a lot more constrained and focused to the domain of interest, given that that's the set of data that you have fed in. And, to that extent, the confabulations will go down as well and so on. What RAG would not do, the plain RAG, is explore the possible relationships that may exist in this, narrowed set of data that you may have given to the RAG system, given that these relationships hold important information, right? Because, and these relationships themselves are not manifest in the vector spaces by themselves. It's like you have to tell, okay, this vector and this vector are related, and that relation itself is not part of the manifest encoding itself. And that has to be deliberately built. And that is the layer that you are bringing to table with the graph, and separately, through additional computation that you achieve that. Once you have that, you have the basic vectors as were available to the basic RAG. Now we have a layer of relationships that exist. So not only, you have identified the entities that can carry these relationships, you have also given the relationship a manifest, a handle for the subsequent step of generation, so that the generation phase navigates between entities through valid relationships that are meaningful to the end consumer. And so in that sense, you have vastly improved upon what you can get out of the same underlying corpus. And this is what graph RAG, delivers to you. And later on, hopefully, if we have time, I want to draw a distinction between plain RAG and a knowledge graph RAG, which similarly adds another layer of important additional value. And I'm pretty sure the world will go there, to eventually from graph RAG to knowledge graph RAG. But I will, stop here for now. And so with graph RAG, you are definitely you will get the comprehensiveness of covering the corpus. You will get the, the diversity, because that now you are able to traverse, newly that was not there before. And the decisions will be a lot more informed. Another dimension to the information that is already embedded in the same underlying data. I'll leave it there. Yeah.
Thanks, Prasad. So Prasad already mentioned, again, some keystone concepts that may be common ground for all of us in the panel, but I think it's worth sort of defining them. So he talked about a number of things. He talked about entities, he talked about relationships and nodes. So since we're talking about graphs, I think it's worth bringing into the table that the key concepts in a graph sort of obviously would be nodes and edges. So you have concepts, entities, whatever it is you want to call them, and ways in which they are related. So you have, these are your concepts are the nodes, and the ways they are related are the edges or relationships. If we want to talk like, if we want to go like one level above one level of sophistication, let's say, and start talking about knowledge graphs and the like. So Matteo, I think you're probably the best person to address that question. So fine, since we're talking, Prasad already outlined the value that leveraging these relationships and these edges between different nodes or concepts bring to the table. So I guess the real question is, how do you define those relationships, and how do you how do you leverage them in GraphRag? So basically, how do you create the graph in question that GraphRag is going to utilize?
Yeah, let me take a step back maybe, because when we talk about RAG, we talk about a particular application pattern that people use in LLM-based applications. The reason for that is because people are starting from the LLM world. They stumble across problems that we mentioned, for example, hallucinations, and the fact that, for example, if you talk to a base model, let's say you take Llama 3 and you ask questions to Llama 3. Now, of course, Llama 3, like any other, has been trained on a portion of the web, on a portion of publicly available data. What if you need to ask questions that can only be found within your organization, for example? Maybe because they are under intellectual property, maybe because they are new concepts that nobody talked about anywhere, or maybe because they are private or secret or whatever. So this is why people started thinking about RAG, which is nothing else than doing information retrieval. In other words, making a query to a search engine, get relevant results relevant to your query, and copy-paste the answer of the search engine to the prompt before giving it to the LLM. So in other words, it's incredibly simple. You are asking not just the question on its own, but the question with a bunch of facts coming from your own private knowledge base. If you think about RAG in these terms, RAG doesn't seem like nothing special anymore. It's just the fact that you are enriching your prompt with special knowledge that only you might have coming from your own database. Now, your own database can be a bunch of documents. And when this is so, we call it, as you call it before, vanilla RAG, because it's the first one that people came about with. So you have a bunch of PDFs, for example. You index them into a vector search index, and you use them to do the RAG. But in the same way, instead of PDFs, which is an example of unstructured content, you can apply the same pattern to structured content. So to a SQL database or to a graph database, which could be property graph, RDF, triple store. It could be another type of, there are many types of graph databases, but the nature of the pattern is always the same. You make a query to a knowledge base of your choice that you have. It can be structured or unstructured. It could even be an API that your organization has available internally. And then you take the answer and you give it to the LLM to say, okay, here's my question, and here are a bunch of facts that can help you answering the question. Now, please answer the question for me. So from my point of view, sometimes I tend to think that maybe we can take a step back sometimes to understand these concepts better and forget for a moment about all the sophistications, because of course there is vanilla RAG, then there is graph RAG and structured RAG and confirmation RAG. There are dozens of types of RAG, but in a sense, it's always the same pattern. It's always the same technique, and the variation is more on the quantity rather than the quality, in a sense. Now, why? Now, having said that, there is a sense for which graphs are very good, at least for some people, and I have the same opinion, why graphs are good for RAG. And I think the reason is that if you only use unstructured content to take the bunch of facts to give to the LLMs, so in other words, to do the RAG, the unstructured content normally presents itself like a list of chunks of text containing still a lot of noise. So even if you do a very accurate search, what you get back from your search engine, from your vector search, which is the first step of the RAG, normally contains a lot of noise. Whereas with a graph, normally what you get back are nodes and edges which can be serialized as triples, subject, predicate, object. Things like, I don't know, Matteo Casu was born in 1984. This is a very atomic, very clear, very simple fact that you can give to the LLM as it is, and it doesn't contain any noise. It already contains only the data that you care about. So, so this is the first reason: the clarity and the atomicity, if you like, of the triples coming from a graph, unlike what you get from a long document full of noise and unnecessary words. Second reason is the fact that a graph is very easy to navigate. So you can do multi-hops from one node to the other using the relationships between things. And so if you have a question like, I don't know, what cities are important for Matteo, you can ask the graph, okay, where was Matteo born? And also, where did Matteo study? Where did he meet his friends, etc. And if you have this information in the graph, with just one query, you can get all this bunch of information in one query and get a bunch of triples very neatly describing what you care about. And then you give it to the LLM so that the LLM will know. So this would be my answer why graphs are good companions for RAG. And I would also add, in conclusion, that I think RAG is the first step towards the idea that LLMs, and I think here I'm going towards Jorge's point of view of things. If we were able to let LLMs be used only in their natural language interface capability and don't use them as databases. So if we had a way to let LLMs forget anything they know about the world and only use them as natural language able interfaces to talk to our own knowledge bases, then we would probably have the best from LLMs. It's a bit of a paradox maybe, because many people think that LLMs are great because they can do work for us. I think that the best thing about LLMs is their capability of using language, but not so much about telling us things of the world, because our things of the world can come from encyclopedias, can come from our own documents, our own graphs, in this case, etc. But sorry, maybe I even talked too much, and that's it.
No, I totally agree with that last point, and that has been my impression on. That was the thing that impressed me the most about LLMs since the moment I got to play with the first one, which was before ChatGPT, by the way. But that's for me the most important, the most impressive aspect, the fact that you can somehow use it as an interface for natural language interaction with your backend, whatever that backend is. It may be documents or a database or whatever. It's something that people have been trying to achieve in one way or another for a long, long time, and LLM seems like a very good way to do that. Okay, would you like to add something to what Matteo said?
Yeah, just one thing, which is that I think that one of the things that is implicit in what we're talking about here, but I think we should call it out, is the fact that language is always understood in a particular context. So the words are never neutral. They're never independent of a context. And when Matteo was talking earlier, he used the example of, when talking about vectors, used the example of queen as being something that is defined as a king minus male plus female, right? And that might be the way that the language model has been trained has been with that understanding of the word queen. Now, there's a rock band called Queen, right? And that is a completely different use of the word queen. The original meaning, or if you want to use the word original, right? Like the original meaning of the word queen kind of plays into the name of the rock band, but maybe in the context that you're using it in, you're referring to the rock band and not the role of a queen, right? So where graphs help with this is that you can have a data structure that says queen, that is a node, that is a type of, that's a concept in our data structure, right? Queen. And then you have this other concept, rock band, and you can associate those two things, and you can say queen is a rock band, for example, right? And you're in some ways you're saying when dealing with ideas in this particular context, we're going to use this specific meaning for this term, right? And I think that you can imagine how specifying relationships between terms at that level will lead to more meaningful results, because all of a sudden you're layering all of this context in that would otherwise be either implicit or would have to be surmised by the system.
Yeah. And I think that's a perfect segue to turn to Prasad, because Jorge, what you just described is basically semantics. You may not have called it by that name, but that's what it is. It's a standard example. Well, actually, the standard example that people use is Apple. So there's Apple the fruit and Apple the company, but Queen does that just as well. There's Queen, the Queen of England, and there's Queen the band. And how do you make the distinction between those two? You can't, actually, unless you have semantics. Otherwise, all you have is like statistical relationships, would tell you not much. If nothing, at least they don't tell you much. So, and that's something that I also wanted to add myself to what Matteo was saying earlier, because what he was describing about, having this, he was basically talking about having some sort of structured graph, not just you can have a graph as a data structure, so okay, I have edges and I have relationships, and you can represent the same information that you represent with vectors using graphs, but that doesn't necessarily mean that you have semantics. And if you don't, you cannot have this type of distinction that Jorge just touched upon. So, Prasad, I wonder if you have any experience working with GraphRag, not just using graph as a data structure, but also adding semantics to it.
Well, as a company, our company's name is Lead Semantics, so I must know a little bit about that. I'm glad you called me out on that. So let me take a step back and kind of draw a connection between language and knowledge. In a lot of our discussions and in the marketplace, and maybe it is generative AI and LLMs doing it, and knowledge has always been kind of on the back foot because of the way it has been used in so many contexts. And I like to use the term, it has been degraded to what exactly it actually connotes, so to speak. Knowledge is everywhere, where it should not be used. Information, knowledge, and all of those things kind of really don't get defined very well and used only in the defined ways that they are meant to be understood. Now that thing said, the language and knowledge, how they are related, is the way I would start off saying is that language has come about only for the strict purpose of communicating knowledge. If there was never a need to communicate knowledge, there would not have been language in the first place. The sole purpose of language is to communicate knowledge. And whenever you see language manifest in the strings of whatever the encodings that we see in different literal languages, they are carrying knowledge. And so the string of words that you see in sentences and paragraphs and narrations, they are carrying knowledge, and you would have to do a process of extraction, so to speak, whatever that may be. What is that knowledge that is embodied or embedded in this string of language? And when you extract through some process, as a human being, we are interpreting what we see and we receive, right? That interpretation, what it does is, it is in one shot, it is extracting and assigning meaning to what the human mind has extracted and has made sense out of the strings of language that it has seen. And meaning itself, now we are trying to automate that, because now language is being generated. Now we want to extract knowledge and make some kind of an algorithmic access to this knowledge. Now, what is that structure into which this knowledge that you extract would be better positioned to kind of service that need? That is where semantics come in. The semantics are the meaning and giving it the structure. And semantic technology is the one that kind of literally translates that to all the things that you can apply algorithms on and so on. And so in that sense, we are elevating human understanding to the machine understanding, because machine is able to extract the knowledge into the same structures as we would. And again, this is factual knowledge that we are interested in. Factual knowledge, by that, is can be subjected to logic, and you can come up with saying whether this is right or wrong. It's like propositional in that sense. So a proposition can be true or false, and you can apply all that kind of thing in an algorithmic fashion, and hence the automation of extraction of knowledge from all this language. So knowledge is an independent artifact, independent of language in and of itself, and the focus is on the language and the generation of words and so on and so forth. But the knowledge is kind of incidental, and it kind of gets this secondary rub, if you will. Whereas it has through semantics, you are really promoting that into its own, and which is fundamentally unbeknownst to all of us. That is what our goal has always been, is to get to that knowledge from all of the exercise that we go through. Because once you have the requisite knowledge, that really sets you in a good position to make the decision or an action. Without that requisite knowledge, we are not really doing anything. And that may be subliminal, subconscious, unbeknownst to us. That's what is happening. And because it is internal, and it kind of gets mixed up in the language, and all that, and another layer of language and another layer of language. Whereas if you stop to think, generated language and then how you extract knowledge, the connection is through semantics. Hopefully I made some sense there.
Okay. I was just wondering when I heard you reference, machines extracting knowledge. I think I have a bit of an objection there. So I mean, what machines can do, and specifically what things like parsers can do, they can extract tokens or parts of speech or that kind of stuff, which you have to specify in advance. Otherwise, well, you can extract statistical relationships, you can extract, I don't know, characters, but not really knowledge. I wouldn't call that knowledge.
Yeah, just to absolutely, and clearly, just extraction alone has no meaning at all. So you are extracting, like, for example, even recognizing a word is one step further than just a series of characters. Why did we choose something to be a word? Because we knew something to be a word from a data dictionary of sorts. You have a vocabulary of these 50,000 terms or tokens, and something matches this token is something that you detect as what you found in the text. Similarly, the meaning as well. Statistically, vectorization gives you a sense of what you found as a token. It has a vector equivalence of it, and if it has similarity to something that you already know, then you assign whatever that you would have normally assigned to what you have in your database. It is that sense of extraction. That is what is happening.
All right. So I think with that, we've pretty much come to the part where we talk about this sort of bridging the two worlds that Matteo referred to earlier. So we've already mentioned, well, Matteo mentioned also previously, these relationships, these explicit relationships that you can add to your graph. And Prasad just talked about, well, and we talk about extracting tokens or recognizing words. So in my mind, the one approach represents like a top-down thing. So a human curator explicitly defines these semantic relationships. The other one represents a bottom-up approach. So you have like parser, scan lots of text, and try to come up with some relationships. Matteo, in your experience, have you seen these two approaches being somehow used in combination, and more specifically to the topic at hand, in building a graph that can then be used for graph RAG?
There are probably two different angles. I think in terms of bridging the gap between statistical and symbolic, we are still ongoing. I think we are not there. We're not completely there yet. To make a metaphor, I could say that if I look at the table in front of me, my cortex sees the raw data, so a brown color, 4 legs, and maybe a kind of texture, etc. And then the rest of and that's the sub-symbolic part. And then the rest of my brain, the symbolic one, will say, oh, that's a table. So I expect to find the chairs, and maybe it's an office table, maybe it's a home table, and make all these connections. So I think in terms of these two things, they are there all the time in the way we function as humans. But in computation, we can see that perhaps this is always present, but maybe it's not used at the business level as much as it could be. For example, we have time series databases. We have databases collecting raw data all the time. Then this raw data sometimes is organized into more symbolic structures that then are manipulated and connected one to the other. But it's still developers defining these structures, right? Or there are machine learning algorithms that start from vision, from patterns of colors, and say, oh, that's a cat, or that's a banana, or that's a table, etc. But these two worlds, are all these features, all these computational achievements that we've made, are still somewhat disconnected one from the other, I believe, in the sense that we could do better at that, in the sense that we don't have, or at least I don't see yet, this connection between the sub-symbolic and the symbolic as something that many people know and talk about and make part of their day-to-day kind of job. The other part of the question was perhaps more about RAG itself. I think, again, one thing is to distinguish the various cases. For example, Microsoft came out with a branded piece of technology that they call Graph RAG, and it's their own branded technology. And we have to pay attention there that what they mean by Graph RAG there is a specific method that they developed and released as open source, but it's one specific approach to it. And what they do is to build a knowledge graph from text and then do RAG with the result. And this is quite good for anyone that doesn't plan to build a graph from their own pieces of knowledge, or for someone that maybe doesn't know or doesn't have the time to do it. But for example, in our case at Semantic Partners, we partner with people working with knowledge graphs, and we have as clients people having a knowledge graph already in their organizations because they do data curation, data quality around them. So for us, the use case of extracting a knowledge graph from text is less interesting, just not less interesting in general, but less interesting to what we do on a day-to-day basis. And so in our case, the graph is most of the time either manually curated or extracted from structured data that is already structured. What I don't see yet, but I think it should come, and it will come, it may come very, very soon, because we have all the ingredients. We just have to do the step in our mentality to do it, is for people to consider normal to take raw data, have some kinds of patterns coming out of that and then match these clusters to existing concepts from existing graphs. For example, standard graphs, because many domains has standardized schemas, standardized thesauri or ontologies for a given domain. So I think this is potentially possible even today with the technology that we have, but in terms of sociological component in organizations, this is not so easy to implement, because you need to make it part of your strategy, it must become a normal thing to budget for and to plan and devise, etc. And this is perhaps still not happening because the two worlds are still a bit separated.
If I
Thanks,
may
Matteo.
continue, add on to
Sure.
what Matteo was saying. Yeah.
I would just
So,
like to point out one thing before you go, Prasad. We have like about 4 now minutes. So my plan was to just ask each of you to do like a closing statement, and then we have to go. So you go first, Prasad.
Sure. Just in continuation to what Matteo was saying, unstructured data, which is like a large part of it is text, and it could be anything else unstructured, can vastly can hold a lot of knowledge. I mean, in fact, as I was saying early on, language is there to communicate knowledge, and so text, wherever it exists, holds knowledge. And so, to that extent, extracting knowledge from plain text is very valuable, and that's what we do as a company. In fact, our product text still does that. And extracting from plain text, the essential components of knowledge, which are entities and relationships, is all the technology exists. It's very mature, and the entities and the relationships are what are being described in the narrative language already. If anything, the structured counterparts like a database and so on, indeed came about because the original knowledge was coming through to them through some human process from an unstructured source. The data in the primary world is like largely the 6 senses that are 5 senses that we have, and those kinds of data that one way or another has been curated into a structured format, and then that is being fed into a knowledge graph. Whereas now the technology exists to take the unstructured directly and to put it into a knowledge graph. And so that allows for all kinds of interesting things, because knowledge is a very valuable artifact. It's in a end destination in itself. And graph RAG is an interesting big step up from regular RAG, and knowledge graph on top of it, through ontologies. And Matteo, you alluded to that, the schemas that exist in organizations is an ontology in the case of a knowledge graph. And ontologies allow for you to kind of extract the knowledge that is already being carried through these unstructured data. And so knowledge graph RAG is definitely the next step forward, and we have been doing it for the last 2-3 years. It's very practical. It is most valuable, already. So I'll stop there.
Thank you, Prasad. So I guess it's kind of obvious what is in Prasad's and Mateo's wish list for the evolution of RAG. What about you, Jorge? What would you like to see going forward?
I think that the key here, and I started by saying that I was interested in thinking about what this is all in service to. The key here is that there is a difference between data, information, and knowledge, like Prasad has been saying, right? Data becomes information when it helps us make better decisions. And that always happens in context. We understand things differently depending on the things that are around them. And the reason why I think that combining RAG with knowledge graphs is so powerful is that it allows us to be explicit about the context for data, the context for the information that we are perceiving. For me, this is clearly where information architecture needs to evolve toward as we move to create these systems that allow us to interact with algorithms that language very effectively. I'm using language as a verb there, right? Systems that language effectively we're going to get so much more use out of it if we can explicitly set the context in which these conversations are happening. And I see the introduction of knowledge graphs into RAG as a very powerful way to do that. I'm very excited about it.
Great. Great. Well, thank you all, gentlemen, and thank you everyone who joined for this session in the audience. I think it's pretty obvious that we could go on and on, but I think this is about time we have to sign out. So pleasure hanging out, and thank you everyone for the conversation. And for everyone joining the audience, I think there's still some, or more than some actually, sessions. So I hope you're energized and you have enough stock of coffee or your favorite beverage, because there's still stuff in the list. Thank you,
Thank you, George.
We'll